Good morning, everyone. Today we'll study the stability concept for nonlinear system. And okay, so this topic is quite different from what you know about the stability for linear system. And this topic is important because normally every system in real life is nonlinear. So we need to know how to determine we need to know the process so how to determine the stability of a nonlinear system. Now first of all, what is mean by stability? Now see, stability means, suppose if you have designed a system. Now stability of that, if we can say that this system we have designed is stable if and only if its output is matching with our desired response, provided input must be a bounded input. Okay, we'll discuss later more elaborately. Now see, the motivation of this topic is, see, the eigenvalue analysis concept does not hold good for nonlinear system. It says eigenvalue analysis does not hold good. It does says that eigenvalue analysis is not applicable. It says that for some function, some nonlinear system, this eigenvalue analysis, we can use eigenvalue analysis, but in that case, it may have some difficulty. So that's why eigenvalue analysis concept does not hold good for nonlinear system. Now we know what is the difference between linear system and nonlinear system. We know if a system doesn't follow the homogeneity and superposition theorem, then we call it a nonlinear system. Now, nonlinear system. Now, in case of linear system, we have only one equilibrium point. And what does that mean? Equilibrium point. Equilibrium point means it is nothing but an operating point where the effect of the disturbance, the net effect of the disturbance is zero. Means suppose we have a motor who's operating at suppose 240 volt, and suppose current is 5 ampere. Okay. Now, if the motor is assumed to be linear system, then we can say that if the motor is operating stable at 240 volt 5 ampere, then it is stable at 220 volt, or it is operating at 220 volt or 210 volt or anything. Okay, but it is not in that case because actually motor is a non-linear system. That's why it may stable for 240 volt, but it may not be stable for 190 volt. That's what we said. Non-linear system can have multiple equilibrium points. And limit cycle is a different topic that we will discuss in different classes. The main point is equilibrium point. So again, what is equilibrium point? Equilibrium point is the operating point where the net effect of the disturbance of the system is zero. Okay. Now third is a stability behavior of nonlinear system need not always be global, unlike linear system. That's why I'm saying a linear system, if it is stable in a particular operating point, we can say that it is stable at the other equilibrium point also, provided the input is bounded. Now, in case of nonlinear system, for the same input, the system can be stable for a particular operating point, but it may become unstable if the operating point changes slightly. That's what it said. The stability behavior of nonlinear system need not be always global. Okay, and so we need a systematic approach that we can be used for this. That we can be used for determining the stability of a nonlinear system. Okay, now next slide. See, what why we are more interested in stability. So see, suppose if we design the system and it is not stable, then what is the importance of designing their system? So basically, an unstable system is useless. Okay. So we need to determine we need to know the process of how to determine the stability of the system. Okay. Now see, the system is a BIBO stable. BIBO means bounded input. BIBO means bounded input, bounded output. Now, a bounded input means if the input you're applying is absolutely summable, the absolutely Summable. Absolutely. Suppose ut is input, mod of ut is less than infinity. Mod of ut means the sum of the sum. The input is less than. That means it has a finite value. Bounded input means it has some finite value. Suppose you have to consider exponential decaying function. Exponential decaying function, so it has a finite value at nearly equals to 0. But if we consider exponential increasing function, we cannot see it bounded because at infinity or in steady state, we don't know the value of the exponential increasing function. But in case of exponential decreasing function, we know that at a steady state or at infinite time, the value is nearly equal to 0. So that is the concept of bounded input now. And so bound Vivo stable means bounded input, bounded output. Means if we have designed a system and if the input is bounded and output is bounded, so output bounded means that the output will have some definite value, which is less than infinity. That means absolutely it must be absolutely summable. Okay. Now, so if we have a bounded input and output is bounded, then we call the system is stable. But one point should be kept in our mind is that if we get a bounded output, if we get a bounded output without knowing the knowledge of the status of the input, means whether it is bounded or unbounded, we cannot say the system is stable. I'm repeating once again. Suppose you have designed a system and you don't know the input condition, means whether the input is bounded or unbounded, but we are getting the output from the system as bounded, then we cannot say the system is stable. Okay, that need to be keep in mind. Okay, now same this is for continuous system, this is for discrete system. The summation of these GQ is for impulse response, or the sum of the function of discrete system is less than infinity. Okay, now see, the here we will discuss the equilibrium of nonlinear discrete time system. So as I've said, equilibrium means the system is in equilibrium means the net effect of the disturbance operating on that system is zero. And this equilibrium is come in concept when there is no input present. Okay. So equilibrium is defined as a condition, as we see. Equilibrium is defined as a condition. Defined as a condition of which system remains indefinitely, means the system remains in that operating point or that position unless it is disturbed. So if a discrete time to describe, this is the difference equation, and if there is a nonlinear difference equation in case of discrete system, x of k plus 1 is the next state. This xk is the present state, xk is the present state, uk is input, this x of k plus 1 is the next state. So this equation is nothing but a difference equation, but non-linear. Okay. Now, now as we show at the equilibrium, at equilibrium, we say we have seen that equilibrium is system is in equilibrium, it's remaining indefinitely, means it operating point will not change if it is an equilibrium. So these present state and next state will be same. Present state and next state will be same if it is in equilibrium. So that's why we've taken if the equilibrium point is xc, xc denotes equilibrium state, then this present state, so this future state and the present state are same because at equilibrium system remains indefinitely. So x equal to f of x plus v of x ut, and we, as I have said, the stability concept, the equilibrium concept of system is comes when there is no input. That means here the equilibrium, you are typically interested in the equilibrium for an unforced system. Unforced means when there is no input, is UK is 0. So x equal to f of x. Okay, next slide. In mathematics, if you talk about mathematics, in mathematics, these x will be called a fixed point. This x will be called fixed point because this point, this operating point will not change if it is in equilibrium state. That's why in mathematics, this such equilibrium is known as a fixed point. Now, note that the behavior of the system in the vicinity of the equilibrium point determines whether we classify the equilibrium as stable or unstable. Now see, what is the meaning of this statement? The statement is, suppose the system is operating at a point, operating point, equilibrium point, where the net effect of the disturbance on the system is zero. Now we can say that this equilibrium point is stable or unstable upon or after we determine the performance of the system near this equilibrium point, near this operating point. Suppose you have a motor which is operating at 240 volt and 10 ampere. Now this is its operating point, equilibrium point. Now we can say the whether this motor is operating stable or unstable. Then we need to find out the motor operating at 230 volt and suppose to 3 or 4 ampere. So in that case, if it is stable, then we can say that the motor is operating at a stable, operating at stably. So that's why the system, this is the meaning of the system. The behavior of the system in the vicinity means in the close range. The vicinity of its equilibrium point determines whether we classify equilibrium as stable or unstable. For a stable equilibrium, we expect the trajectories of the system to remain arbitrarily close or to converge to the equilibrium. What is the meaning of this? Means these for a stable equilibrium, the trajectories of the system means nothing but the response of the system to remain arbitrarily close or to converge to the equilibrium. Means the response of the system should follow the response um, to the response when it is operating at equilibrium point. Okay. Now, next. Now, to also, as I have told earlier, that to determine the stability of nonlinear system, we need to have some systematic approach. So here is one of the approaches: Lyapunov stability theory. Lyapunov stability. So it has some statement. What is that statement? Lyapunov stability theory is based on the idea that at a stable equilibrium, the energy of the system has a local minimum, where at an unstable equilibrium, it is at a maximum. Now see, here we have taken only the energy as a parameter. It is not necessary that energy should always be taken as a parameter. Okay. Now, that is not important. Here the important statement. The Lyapunov stability theory is based on the idea that a stable equilibrium, the energy of the system has a local minimum. That means at the stable equilibrium, the energy of the system should be minimum, as a local minimum. That is a finite value. It has a finite value. Whereas unstable equilibrium, it is maximum, means it will not have any finite value. Now, it is an energetic, and it can be of any function. It can be of any function. That's why this property is not restricted to energy. That means it can be of any function and is in fact shared by a class of function that depends on the dynamics of the system. Now, what does that mean? Now, dynamics means the response of the system. Dynamics of the system means the response of the system, means how the system behave when its input gets changed or when there is some disturbance. So, the so this Lyapunov function. This is the Lyapunov function. So, at the functions that depends on the dynamics of the system. So basically, to determine the stability of a nonlinear system, we first, by this Lyapunov stability method, we first find out the function, find out the Lyapunov function. That is the function system that depends on the dynamic of the system. Okay. The next slide, we will see how to determine the stability. Now, see, Lyapunov function. If Lyapunov function can be found for an equilibrium point, then it can be used to determine its stability or instability. This is particularly simple for a linear system, as you know, because a linear system is very easy by this transfer function model, this pole concept, and the state space model by the eigenvalue concept. But it is complicated for a nonlinear system. Okay. We begin by examining properties of energy functions. We will take energy as a function to generalize that the concept of Lyapunov stability, and then we will draw a conclusion. So first thing we need to keep in mind, the energy is a non-negative quantity. That means energy cannot be a negative value. And second, this energy continuously changes of the system. Okay. Now before going into detail, we need to have some we need to know the some terms like the positive definite, negative definite. Okay, now uh, see, call functions we call functions that are positive except at the origin. We call functions that are positive except at the origin. So uh, here we will try to gather information about some functions. Namely positive definite, positive, negative definite, positive semi-definite, negative semi-definite, etc. Okay, that's it. We call functions that are positive except the origin is positive definite. What is the meaning? We'll see in the next slide. See, a scalar function Vx, scalar function V of x, we can choose anyone, but this is as a general nomenclature purpose. A scalar function V of x is said to be positive definite if V of 0 equal to 0 and V of x greater than 0 for any non-zero x. See in the previous slide, we call functions that are positive for any value of that parameter except at the origin, that is positive definite. That is the reason. Positive greater than 0 means positive. So function v of x means the value of this v at any value of this parameter greater than 0 for any non-zero x, and at that origin it is 0. So that is called positive definite. Now if it is less than 0, if it is less than 0, it will be called negative definite. Okay, and if this greater than sign change by greater than equal to 0, then it will be called positive semi-definite, and it is called less than equal to 0, then it will be called negative semi-definite. All are written here, and if none of these four conditions satisfied, then v of x will be called, this function will be called indefinite. So it will be called indefinite. All are written here. Okay, now scalar function Vx is a Lyapunov function region D if it satisfies the following condition. Now, scalar function will be called a Lyapunov function, which depends on the dynamics of the system. There is Lyapunov function in a region, suppose D, if it satisfies the following condition. The conditions are Vx is positive definite, and and this V of x decreases along the trajectories of the system. That means suppose if we're talking about suppose you're talking about energy, that means if energy is positive, definitely it is always greater than 0, and the energy suppose decreases along the trajectories of the system, and that means when the when the input to a system changes, the system will get disturbed, and it will try to attain a new state. That means it will be in transit. Now, for a stable system, the transition should die quickly and should reach to 0. That is the meaning of here. It decreases along the trajectory, means the response time, the response of the system. Okay. So suppose the del of V of k. Del of V of k means the change in the two state. Change in the two state. This is the present state and this is the future state. Now, suppose this is the difference between the two states. This is present, this is future. That means now if it is less than 0, if it is less than 0, that means the value of the future state is less than the value of the present state. That means as the system response changes with respect to time, as the time increases, the value of this future the value of this future state is less compared to its previous state. That's why it is less than 0. That means as the time progresses, this future state will get the value nearly equals to 0. That's why this term is less than 0. That means you can say the system is stable. But this is as a local stability. This is as a local stability. But you need to know the global stability theorem. For that case, you need to add an extra point here. See, these two are same for a global stability. For a global stability, this is for local stability. For global stability, you need to an extra condition, which is that condition is it is radially unbounded. Radially unbounded means uh, the the dynamics of the system. The dynamics of the system includes more parameter or includes more system condition to into its response. So when it get disturbed, okay. This is stability theorem. So what is stability theorem? So before going into stability theorem, we need to prove this one. Suppose you have taken an example, the equilibrium point x equal to 0. Suppose this is a nonlinear discrete system. We need to uh, prove that this equilibrium point x is equal to 0 is asymptotically stable. Asymptotically stable. Now, what is meaning of this? This del Vk, as you know, previous slide, there is a difference between the present state, the difference between the future state and present state. Difference between the future state and present state. It can also be written as, suppose if you have taken this x of k is present, so x of k plus 1, the next will be future. Similarly here, if x of k minus 1 is taken as present, so its future means plus 1. So plus 1 means it become plus 1, 1 getting cancelled, xk. Both are same. This is present, this is future, this is present, this is future. And for stable, this should be less than 0. That means as motion progresses, the value of V decreases continuously when the transient die out. That's why you can say that is stable. Okay. Suppose this one system is given, non-linear discrete system is given, and these are two equations, two discrete equations. We need to find out the stability. How we can find? See, from these, del V is change between the present state and future state. Here we see del V is x of k plus 1 minus c. Here, this is the present, so this is the future, and this is the present. So future minus present. Future means this term. Future means this term minus present. We have taken why this square because this is the we have taken v of x equal to x transpose into v of x. Okay, and similarly plus this x2. This is future and this is present. So future minus present. We have taken a square function. So if we manipulate and this p1 or p2 or so p1 are the values, some scalar value. Okay, now see if this del vk is become negative, then this system will be stable. If it is not negative, then there is unstable. Okay. Here, in conclusion, there are two Lyapunov method. One is reduced method or first Lyapunov criteria, and this one is direct method or second Lyapunov criteria. First one is for used for find out the stability of a system for a nonlinear stability of a nonlinear system when we when you reduce that nonlinear system to a linear one about its equilibrium point, and then you determine stability by the normal linear method like state space analysis with the help of eigenvalue or these transfer function pole zero concept. And then second Lyapunov method, which one that we have discussed by the this Lyapunov method. Okay, I hope you understand this. Thank you.